get this working. There are a couple of things, though, that will help us. So first of all, before I talk about those, the guy standing all the way back in the corner there with the blue shirt texting, okay, that's Tag McCurdy. He works for the training company through which that's managing a lot of the training for Spark. So if you decide you want to talk to somebody about maybe arranging Spark training for your organization, talk to Tag. He's going to be back there or just outside during a break, or if you're bored, get up and chat with Tag. Now, with regard to, I know some of you are having some problems in performance. So there are a couple things I'd like to explain, and then a couple of other things that we can do to help mitigate some of this. So problem number one, don't try to clone the world right now, okay? If you decide, well, we're going to do these 5 labs, I might as well clone them all over into my environment now. Well, congratulations, you're helping to hammer the back server. Okay, the back-end server is getting hammered with your cloning operations, and all it takes is a few people to do that. So, so the recommendation is, and that includes the Databricks. I actually should not have told you, hey, go ahead and clone the Databricks guide, because I think that actually helped contribute to this, because that's fairly large, right? It's lots of different little notebooks. There is a way to cancel an ongoing clone. So if you're still waiting, for instance, for the Databricks guide to finish cloning, feel free to cancel that, because you can always go back and get that later. That will help reduce some of the back-end server contention, all right? Number two, more than one person said, you know, why is it if I hit Shift-Enter and the Python REPL is just showing, for instance, 1 + 7, why does it take so long? You know, is that actually doing cluster operations? Well, the answer is no, it's not. But that has nothing to do with why it's taking so long. So let's think of it in terms of, what if you were running the PySpark shell on your local machine? Okay, well, what is that really? Well, that's an instance of a Python REPL, either the regular Python command or IPython, whichever one you choose. That's running locally, and when you type in something that is not Spark related in that kind of REPL, it's immediate. 1 + 7 would give you an immediate response, and it would only go out to the cluster if you're doing RDD operations. Right? You do a collect, then of course it's going to go out and do stuff on the cluster and pull stuff back. However, we're running in the browser here. The browser is not running Python or Scala when we look at Scala notebooks, and Python and Scala are not running on your local machine. So in order for those commands, no matter what they are, whether they're Spark operations or a simple 1 + 7, in order for those things to complete, the notebook that's running in your browser has to make a network request somewhere to a Python process in this case, or later a Scala process, to interpret those REPL commands, right? That's not running on your machine. It has to be running somewhere. Turns out it's running in your cluster, okay? It's not running the way a Spark job runs, but there's still somewhere back in your cluster somewhere, there's something that is handling the operations of what a REPL would normally do if you ran it locally, which is why when you hit Shift-Enter, it might take a while. If the network is overloaded, or if the cluster is overloaded, or whatever, there's network latency there. That command has to go all the way back over to Amazon, get executed on the cluster, and come back. I don't even know where those Amazon clusters are. Are they on the West Coast or the East Coast? Not sure where they were spun up. Point is, you can't expect, pardon me, you can't expect on an overloaded Wi-Fi network, when you're running any notebook like this, whether it's the Databricks notebooks or any of the open source ones that are out there, this stuff isn't running locally. There's network latency. So it's not immediate, because the actual code running the REPL is not immediate, right? Your browser would have to be capable of running and interpreting Python or running Scala for that to be immediate, and we're not there yet. Okay, so yes, go ahead.
Just a quick announcement. We hit an issue over lunch that we've addressed. So we're actually going to restart this shard. It only takes a minute. But what that means for you, and all your notebooks and everything are fine, that just means that you're going to get logged off. So you'll need to log back in. So pause what you're doing for a second. And then after, so this issue is related to cloning. And we recently increased the size of the Databricks guide significantly. And that's why the cloning issues, some of the cloning issues we were seeing. So after the restart, don't clone the guide. Clone, I think you mentioned this already, just clone individual notebooks, and we won't run into the issue again. But you're going to get logged off here in 1 second, and you'll have to log back on.
Okay, and then there were some other issues that people had that I need to point out again. If you're cloning something, right now the UI, this is something that I understand the engineering team is looking at better ways to do this, but right now the UI wants you to give the full path to where you want to put that thing. Okay, and I just want to reemphasize, if you were to clone a lab, like the DevOps 101 lab, when you hit the clone operator, what's going to come up is a path that says /todayslabs/DevOps 101 copy, okay? And the DevOps 101 copy is what's going to be highlighted. I would demonstrate it here, but since we're all getting logged off in a second, okay?
You should have been logged off by now, and if you haven't, just click refresh. Hold shift and press refresh to get rid of cached things. You should see your login screen again.
All right, well, let me see if I can bring that up and I can demonstrate what I'm trying to explain.
All right, it's coming back up now, so give it a minute.
Okay, well, I'll just keep mentioning this since I can actually probably show it to you over here, come to think of it. All right, so this is a different shard that is actually running a newer version of Spark, but I can show you what I'm talking about in here. All right, so while this is still coming back up, please just pay attention to what we're doing here, because if you're going to have to clone more things, and this is a very common problem for people to have. All right, let me make this big. All right, so suppose I wanted to, inside this workspace, I want to clone the Databricks guide, which I just told you not to do. Okay, I'm going to click on that, clone. You'll notice what comes up is it says /Databricks guide copy. It assumes I want to clone it into the same place. That's not what you want to do. In your case, you want to say /home/ whatever your user ID is, okay, whatever that is. And then don't just put that. This is not like a Unix copy where you can copy to a directory. You have to give it the name that you want it to be copied to. So you have to have this third part. You could remove the copy if you want, but that's how you have to do this. Problems we were seeing were people trying to copy it to a different copy within the Today's Lab directory. That won't work because you don't have permission to do that. Accidentally copying it into somebody else's home directory, well, you're not going to have permission to do that either. Leaving off the name of the notebook and just putting /home/my folder, well, that won't work. You have to give a target notebook name. Okay, so these are the kinds of problems. You have to pay a little bit of attention to what you type in here. Down the road, it's hoped that we'll have a much nicer UI here, but it's not there yet. So you just have to be a little bit careful where you clone this stuff. And if your cloning never returns, please do let us know. All right, let's see if this is up yet.
It's not up yet.
No, it is not. Okay, we're just going to give it a minute. I'm not going to dive into any more course material. I want you to have more time to play with this lab. Who in here actually managed to get the thing done? Anybody? Okay, so a few of you. Okay, so if while everybody else is working on this, what you might want to do is try to modify some of the commands in the lab, right? Try to get it to do a couple of different things. Try to get it to pull down some different data. You know, they're free to edit.
Yeah, maybe we can just like jump into a lecture and I can work with it back here to figure out what's going on.
Okay. Well, let me see what we've got that we can look at here in the meantime. Okay, well, while we're waiting for this to come back up then, let me switch over to let me switch over to something else that we can talk about briefly. And we'll kind of do this in several pieces. This is fairly easy to break up into different pieces. All right, so this is a different deck, and what we're talking about here are some of the transformations and actions that are available. Now, this is an interesting deck because it's adapted from something that was posted out on, I think it was GitHub a while ago. It's a very graphical representation of a lot of the transformations. We're probably not going to go into all of them because some of these transformations are, well, I don't want to say more advanced, but more detailed than we necessarily want to go into right now. But I like the way that this deck is presented. So here's the guy who wrote the original set of things. So this is Jeff Thompson. He put together a bunch of visual diagrams that depict the Spark API. And Jeff's original work, there's a link here. You guys should have a copy of this. Here's the deck. If you want this deck, it's out at training.databricks.com/visualapi.pdf. Okay, so feel free to download a copy of this. There's some good links in here. So again, training.databricks.com/visualapi, all one word, all lowercase, .pdf. All right, I'll leave that up for a minute. You can get the, you guys all read that? You can read that URL? You see it in the back? Okay. Not sure I can pull it up. I'm not sure that's even a doable thing. Not so much. I think I can give it to you another way, though. Give me a second. That should be a bit more readable. You guys can read that from the back, or is it now blocked by the lights? Let's try this. Heads or lights? Okay, we'll be able to get a copy of this now? We all caught up? All right. Okay, so if you want to look at the original stuff that was used to develop this slide deck, or adapted for this slide deck, Jeff Thompson's stuff is out on GitHub and talked about in a blog post, so it's definitely worth looking at. What happened was that the folks at Databricks got wind of this and commissioned a guy named Adam Brindell to basically take that information and evolve it into this training deck. This is still a work in progress, but it's still pretty awesome and good enough that it will help here. So we're going to go through some of these transformations, okay? And we're going to. This is an example of what one of these transformations looks like, okay? So I first should talk a little bit about the legend. So the legend here is that the things in blue are the original items, original data items out of the original data source, okay? Or data items as they live in a particular RDD. So they might have been transformed by a previous RDD, but this is the original data item as it lives in that particular RDE. If it's a pair data item, in other words, a key value, then the key will be noted in black. What looks to me to be orange and looks up here to be a kind of ugly brown is a transformed type. But it's not just transformed type, it can be a transformed value. So we haven't talked about this yet, but there are certain transformations that remove data, such as filter. There are other transformations that don't remove data but change data. One of those that we're going to look at is a function called map. So you can use map, for instance, to take, let's say you've got some stream of numbers. You could take a map transformation so that you could increment or square or otherwise transform the numbers in there. So there we're keeping the same type, but we're transforming the value. All right, I'm going to increment every number in this stream by 1. I'm not sure why you'd want to do that, but it's certainly a doable thing. So that's a transformation of the value that retains the type. You can also transform the type. I want to take everything in this incoming data stream and convert it from a number to a string. All right, so now we're transforming in effect, we're transforming both the value and the type. A map can do either one of those or both of those, okay? And then another part of the legend is an object on the driver, okay? That's something that's actually running inside the driver that isn't distributed out to the rest of the cluster. Partitions are indicated with these dashes. So if you were to look here, what this basically says is this particular diagram shows an RDD that has three elements across 2 partitions. Okay, and then we've got user functions down here. So a user function is something that takes a piece of input and emits a value. User functions we often think of as being passed into transformations. So as an example of that, we haven't seen these transformations yet, but we will look at them. A map function, remember I just said a moment ago, a map function is transforming the data somehow. It's not changing the cardinality of the data. It's not changing how much data you have, but it's transforming the values. Map is a generic idea. What you give map, in addition to the data coming into it, you give map a function, and that function gets called on every element that gets passed into it. That's the transformation, and you get to choose what that function is. So that's a user function. We often think about that user function as living in the driver, but it doesn't. It's actually sent across the wire to all the shards so that those operations are actually done individually on each element in the cluster, each node in the cluster. Okay, I said shard, I meant node. All right, and when we refer to the emitted value, that's the value returned by one of those functions that then Spark uses to do what it needs to do with the data. We'll talk a little bit about that. Okay, there's some other things in the legend here. These dice indicate some sort of a randomized operation. So for instance, there's a sample action. So a sample action will choose some random data and return it to you. This cute little Venn diagram indicates some sort of a relational or set-based operation. And this graph or roller coaster, whichever you prefer, is some sort of a numeric calculation. Okay, again, these are just the icons you're going to be seeing in here. All right, so once again, Spark operations are broken up into 2 different kinds of things: transformations and actions. Transformations are lazy. So as I said this morning, when you do a transformation on an RDD, you get back a second RDD that has essentially captured that transformation in the series of steps, or often called the DAG, the directed acyclic graph, right? So that's lazy. It's not been evaluated yet. An action is something that forces that graph to be evaluated, that forces all those actions to be taken, that forces the data to be loaded, for instance, maybe from HDFS, forced through all the RDDs. The transformations at that point all get triggered, and then the action returns some value that is sent back to you into the driver. Okay, and this is probably almost impossible to read, but this is, again, another view of some of the operations that are available. So the idea here is that the ones that are, these are supposed to be like Taekwondo or karate belts, I think. The idea is that white is easier. The blue ones are supposed to be sort of medium level. That's sort of an arbitrary distinction, but in general, these are how they're broken out. Here's some general purpose transformations. So again, these are all lazy: map, filter, flat map, etc. These are mathematical and statistical, sample and random split. Set theory and relational based ones are over here. So distinct is a good example of one of those. This sounds an awful lot like the distinct operator in SQL, and it behaves pretty much the same way. And then there are a bunch of these over here that I'm just going to skip for the moment. They're interesting, but they're a little more advanced than we need to talk about right here. Right? And then down here are a bunch of actions. Okay, and again, the blue ones are the ones that you're probably not, at least initially, going to be using quite as much. Okay, so there's also this notion of a narrow and a wide operation. Wide, basically, you can think about as requiring network I/O. Narrow meaning it doesn't necessarily require network I/O, right? It can be done locally to the particular node in the cluster where it's operating. So a map, for instance, would tend to be local, right? A sort would be wide because the sort is going to require moving data across the network so that you can get data that's sorted close together all in the same place. Okay, so that's basically, at our level, that's good enough to understand narrow and wide, although these are the icons that are used to indicate whether a particular transformation or an action is narrow or wide. Okay? So we often depict a narrow one. There are some more formal definitions. With a narrow one, each partition in the parent RDD is used by at most one partition of the child RDD. Okay, so there's a one-to-one mapping. The data is partition to partition. Right, these are the more formal definitions. Don't worry about it if this is a little confusing. Wide is where this kind of thing is happening. Right, you have multiple child RDD partitions that may depend on a single parent RDD partition. In other words, you can think of the partition as potentially fanning out into multiple partitions. And recall that partition equates to the parallelism, right? Each partition is going to potentially run at least either on a different node or within a different thread, but I mean, that's your basic unit of parallelism. Okay, and then there's this notion of lineage. For our purposes, let's just think of lineage as the directed acyclic graph. Okay, the lineage is the set of operations from start to finish that get done. But that lineage, and it's called a lineage obviously because it's a direct line that you can follow, Spark actually uses that lineage in some very interesting ways. For instance, in some deployments, if a particular node in a cluster crashes, or a particular executor within a node crashes, everything it's operating on goes away. Anything that was in its memory buffers goes away. But Spark can use that lineage to figure out how to reconstruct a new instance of that thing and feed it the data that it was processing before. So even though it's going to have to do some more work to catch up, it's going to do the right work, and Spark can use this lineage, this graph, to figure out how to restart a node and get it to come back up to where it was before it crashed. Okay, so here are some examples of some narrow transformations, right? There's map, filter, and union. These are direct one-to-one, right? A wide, it would be something like group by key. Think about what a group by key does. Okay, here's an example of a group by key. I'm going to do a word count. I'm analyzing all the words in a particular huge file, right? In order for me to be able to do that, I have to take all instances of any particular word and group them together so that I can count them, in effect, right? Now, in that particular case, I'm not grouping while I'm counting, but at the end, I'm going to want to group all those counts together. So what I'm doing individually across the network is I'm saying, look, you've got some, let's say that the word is red. You've got some instances of the word red in your partition. Count them all up. You've got some instances of the word red in your partition. Count them all up. And all the partitions are doing that. But eventually, I need to gather all that information together so that I can combine all of those counts so I know how many times the word red appeared in the entire data. That is a group by key operation, and by definition, that requires information to be shuffled across the network. Okay, so that's a wide. All right, let's skip ahead a little bit here. So here are some of the core operations. Right, so here's a map. Okay, these are basically examples. Okay, here's a map. We're not showing the partitions because it doesn't really matter to understand the map operation, right? But let's say we have an RDD and there are 3 items in that RDD. So this is not particularly a big data set. The RDD has 3 items in it. Maybe we've winnowed everything down from 100 million items down to these 3 items. Okay, and for some reason this is not doing what I want here. Okay, there we go. right? So basically, a map works one by one on each item in the RDD. So it transforms one item, which then ends up transformed in the new RDD. Transforms the second item, which then ends up transformed in the resulting RDD. Transforms the third item, which then ends up transformed in the second RDD. So here, the starting RDD is X, the ending RDD is Y. Notice, the important thing to notice here is that the first RDD is not modified. Okay? You get a new RDD with the transformed values. You could still go back and do stuff on the old RDD and you'd have the pre-mapped values. All right, is that clear? Right, so that, I mean, that's the important thing about the way map works. This is a functional way of looking at the world, right? We always transform things into new things. We don't modify them in place. And this is particularly useful for data, right? And data that's coming over the network. You can't really go modify this stuff in place. So you're transforming it and winnowing it down and getting new things out of it, but leaving the old things untouched. Okay, we'll do a couple more of these and then we'll step back to the lab. Yes? When you do an operation like a map, does it keep the same number of partitions? Yes, I believe that's true. Yes. You can always change later, but I'd have to look at the actual map operation to say I'd like to do a map. It might be that it supports, I'd like to do a map and change the number of partitions while I'm mapping. I'd have to go look at the API to see if that's the case. It's not entirely clear to me why you would want to do that, because if the data is partitioned in a reasonably efficient way and you're not changing the cardinality of the data, then what's the benefit of repartitioning it? Right? There may be a benefit if you're mapping of it. It could be that you're mapping things and changing a key space, right? At which point you might want to repartition it at that point. You'd have to, that would be a per data set type of thing. You know, whether you want to repartition it, get wider partitions, or reduce the number of partitions. Okay, so here's an example of this. Can everybody read this? Right, so there are two ways that this can be done. If you don't understand Python, then don't worry too much about it. But basically here, we've taken a collection of 3 items, B, A, and C. All right, what does parallelize return? It returns an RDD. So X is an RDD. X contains those elements split across some arbitrary number of partitions that I'm not telling you. There's some default number that parallelize uses. I think it's 2, but again, I'd have to look it up. All right, then we do a map on it. Now look what map is taking. A lambda in Python is a one-line function. Okay, so if you're not familiar with Python, just read that as, this is a function taking an element in, colon, and returning what's on the right-hand side of the colon. All right, so given a z, it will return a z, a tuple of a z and a 1, and a tuple is just an aggregate of 2 values. Okay, Python supports tuples, so does Scala. Java at the moment does not, right? So a tuple is sort of like a read-only array of a fixed size, right? And then we're going to do a print of the collect on X and a collect on Y. So the question is, what do those things return? So you can see here's X over here. If we do a collect on X, here are the values in X, B, A, C. Note that they came back in the same order we put them in. That's not guaranteed, right? Depends what your cluster looks like, depends where things are, right? And then here's the second one, B, A, C, but they've been transformed into these tuples where you've got a 1 associated with each one of them. Okay, turns out this pattern is actually fairly common. This is how we do a word count, right? Every instance of something is transformed into that thing and a count of 1, which then we can sum later on, right? And the Scala version of this is very similar. We start with an array of BAC. The Scala syntax for what amounts to an anonymous function, sorry, hit the wrong key, is this, this fat arrow syntax here. This basically says I expect an argument called z, and I want to return a tuple of z, comma 1. The lambda syntax in Java 8 is similar to this. It uses a narrow arrow, right, not a fat arrow. What's happening here in Scala as well is that the type of z is being inferred. Okay, so in this particular case, the compiler can look at this and say, you don't have to tell me that Z is a string because I can infer that from the inputs, which is why we get this terse syntax. But essentially, you can see that the two APIs are very, very similar. There's not much difference in either usage or brevity. They're both about the same. All right, so that's map. We'll look at map and filter, and then we'll set this aside, and we'll go back to the lab. I'm going to stop at filter, because map and filter are probably two of the biggest operations you do on data, right? I want to transform this into something else, and I want to get rid of some of the stuff in there I'm not interested in. So we'll compare and contrast these two, and then we'll jump back into the lab. Andy, stuff's up now, right? Okay, good. So, so filter is the same kind of idea. You're going to be operating on one element at a time. So you start out with an RDD of some number of elements. Now the difference with filter is that, once again, the filter operation takes behavior. Okay, this is another functional programming notion. You can parameterize in functional programming languages or languages that support this kind of interaction. You can parameterize a function both with data and with behavior. Parameterizing a function with behavior we do by passing another function in. Okay, the easiest to understand example of this is a sort function that allows you to pass in another function that figures out how to do the sorting, right? So that second function, the comparator function, then is behavior. In Java, we typically do that by passing an object that implements some sort of comparator interface, but the essential behavior is the same. You're passing that guy in so that it can make decisions on how this stuff ought to be sorted. It's just that languages like Python and Java, so Python and Scala, allow you to do this in a much more succinct fashion than the way we have to do it in Java. So the idea behind filter is I've got a set of data. I want to keep some things, and I want to throw some of them away. How do I determine how to do that? Well, what I do is I call the filter operation on the RDD, and then I pass it it's a comparator. Okay? You pass the filter operation a comparator. The comparator will be called with every element in the RDD, and if the element is to be kept, the filter comparator, for lack of a better word, it's often called a predicate, right? The filter predicate, or what I'm calling the comparator, if it returns true, the element is kept. Or, more to the point, the element is transferred to the resulting second RDD. If the filter returns false, the element is not transferred, it's thrown away. Okay, I don't really want to say thrown away, because it doesn't leave the source RDD, right? It's still there, but it just doesn't get moved, transferred, copied, flowed through the second RDD. All right, so that's how filter works. So graphically, it looks kind of like this, right? So if we decide we're going to keep the first element, it gets copied over. Notice the second element here, you can barely see here. It says this emits false. So what that means is the filter was given this second element, made a decision that this one isn't to be kept. Right? Example, well, this is not an error log entry. This is an info log entry. I'm not interested in those. So the filter operation returns false. This guy doesn't get copied, which is what this thing is supposed to indicate, right? And then finally, it gets to the last one. The filter says, oh no, this one I do want to keep. So this one gets copied over or flowed along to the resulting Y RDD. And this is what we're left with. Okay, so before we had 3 elements, and after we had 2. Because filter returned a false for one of the elements, right? So in Python, we're back to the lambda syntax again, right? Now, this particular case, we're starting with a list in Python, or an array of 3 numbers, 1, 2, and 3, and we're keeping odd values, right? So divide by 2, remainder is 1, I'll keep that one. That means the 2 will get thrown away. So what does the lambda do in this case? It says divide by 2, and if that's equal to 1, it's odd, and therefore keep it. Return true. Otherwise, return false. And the Scala one works pretty much the same way. Okay? So this is a graphical representation of map and filter. Hopefully this clarifies a little bit how they work. So at this point, I'm going to leave this up, but at this point, I think would be a good time. The shards are apparently back up. So if you can log in and try to work your way through the Dev 101 lab, right? And what we'll do is we'll give it another 15 minutes or so, and then we'll 15, 20 minutes, and we'll move on. And as I said before, if you did manage to get through this lab before, just like mess around in there, add some new commands, try changing some of the ones that are in there. You can't break anything. If it breaks, it's not your fault. So just feel free to go in there and play around with what's in there and see if, try adding another filter operation or another map operation, see what happens. We've been at this lab a good long time, and some of that is partly because we spent time trying to move people off of the class East 2 to class West, whatever. So what I'd like to do is go through a few more of the slides of the transformations. We won't do all of them, but I want to show you a few more, give a sense of how to read that thing. And then we'll take a quick break. Everybody can get some coffee, and then we'll try to push through the rest of it. All right, so let me find my slides here. Okay, so we talked about filter and we talked about map in here, right? So one of the other ones is flat map. I'm actually going to demonstrate this a completely different way so that you can understand it. Okay, I find this, when I teach a Scholar class, I find this is the easiest way to show people what a flat map does. So the question is that's probably not big enough for you guys to read. All right, can you guys read this from the back? All right, this is a Scholar REPL. The only reason I'm using this is that it's an easy place to demonstrate a flat map, okay? So first I'm gonna create an array here, and this is really an array of arrays. All right, so let's say I've got an array here of these elements, another array here of these elements, and another array here of those elements, okay? So if you look at this, this is an array of arrays. Now I can map this. If I were to map over this, if I were to do something like this, map, and I'm going to pass this guy a function, okay? And there's an element that the function gets that it can do something to, and it can transform that element into something else. What will E be in this case? It's an array, right? Each element of this thing is going to be an array, right? As it turns out, sometimes that's not what I want. And a common example in Spark is, I read and partition a file using SC text file. What gets distributed out to the nodes, to the executors? Lines from that text file. But what if I want to operate on words, right? Well, what I can do is I could do a map on those lines and split each one into a series of words. But now what do I have? I have an array of arrays, right? I've just transformed my array of lines into an array of words, right? And if I want to deal with that in a non-nested fashion, then maybe instead of doing a map, I want to do a flat map. So for instance, if I'm going to change all of these guys in here, I'm going to increment them by 1. So this is a flat map operation. Now this is the Scala version of flat map, but conceptually it's very, very similar to what you'd be doing in Spark. So here, now if I do a flat map, the trick here is that the element coming in, this eliminates one level of nesting, provided I get this right. Hang on just a sec. Let's just do this for now. Okay, I'm not going to add 1 to it. I'm just going to do that. Turns out Scala actually has a much simpler operation for this, but there you get the idea. What I've done here is I've said I've got my array, and if I flat map that array, right now I'm not even doing a map. I'm just flat mapping each element to itself. But there's an implicit flatten operation in there, and you can see what it did. It flattened out all the elements in there, and now I have one array of all the elements that were in the nested arrays. Okay, so that is a flat map operation. So when we're talking about a flat map operation in the context of Spark, that's what we're talking about. I've split, usually it happens because you've split something like an array of lines, set of lines, right, into a nested something, but it's that nested something that you want to deal with, and so you want to get rid of the nesting, and that's why you would tend to use a flat map. Right, so this is an example of it, right? Here's a particular item within RDDX that has 3 elements in it. By doing a flat map on it, whether or not I transform them, I'm actually transforming those 3 elements into 3 separate items in the resulting RDDY. So we have one item starting out in RDDX, and now we have 3 corresponding items in RDDY, right? And this just continues, so that what we end up with in the end of the day is we started with 3 elements in RDDX, but we ended up with 9 elements in RDDY because of the flattening operation, okay? So that's the difference between flat map and map. They're both map operations, but one of them allows you to flatten out a level of nesting. And doing a word count of some kind or a grouping of some kind over a list of lines is a perfect example of that. Yes? Yes. The question was, what if it's nested multiple times? Do you have to flat map a flat map? And the answer is yes. You can't say, hey, flat map, go 5 levels of nesting deep. Okay? And that's true of general Scala collections as well. I believe some of the new Java 8 collections have an equivalent of flat map. In any language I've seen that has this capability, it only goes 1 level deep. All right, so this is an example of what it would look like. Okay, so we start out here looking at just the Python one. The Scala one works the same way. Start out here with a parallelized collection of 3 items, which of course get distributed out into some number of partitions. We do a flat map over it. Look at the lambda. The lambda is a function. It's going to receive an x coming in. That x is going to be one of the items from that list. But this is another use for flat map. Notice what this thing is returning. It's receiving 1 item and it's returning 3. So the flat map is actually returning multiple elements, but they will then get flattened out. So for each x, we're going to return x. We're going to return x multiplied by 100, and we're going to return 42. So when the 1 goes into this, we're going to get a 1, a 100, and a 42. Then we're going to get a 2, a 200, and a 42. And you can see in the resulting list, the resulting y down here, that in fact, even though we were turning these tuples, which are sort of like lists in Python, they're just immutable, right? Instead of it getting back a list of 3 tuples, each containing 3 items, we're getting back a flattened version. We're getting all 9 items flattened out into the list. Okay, this is a useful transform because it saves you, if you do this, it's efficient and it ends up saving you 1 level of transformation. If you had to do this manually, you could do it, but the flat map does that removal for you automatically, and it does it in a distributed fashion. All right, we also have, we're only going to go through a few more of these, but we also have a group by. This kind of works like a SQL group by, right? We typically group things by keys. So here's an example where we have James, Anna, Fred, and John. Okay, 4 elements in the RDD, regardless of the partitions. There are 4 elements in the RDD, okay? And we are calculating a key on John. So what we're going to use, remember I said that the little box up top here is the key. So we're transforming each element into the element plus a key, and the key is going to be the first letter. So clearly the goal of this particular transform is to group things by their first letter. Okay, so when you do a group by, what you're going to get is a new RDD that has a key and a list of values that correspond to that key. It's grouping all variables, it's grouping all values with the same key together in a collection within an RDD. So John goes over here into this item in the RDDY. Fred goes into a different item because he has a different key. Anna goes into a different item because she has a different key. But where is James going to go? Right there. James and John are going to be together. Right? So this is the result of a group by. All right? This is also a very powerful operation. SQL guys know how powerful this is. We use it all the time, right? But Scala guys do as well because there are group by operations on the Scala collections library. It's a very common thing to do when you're trying to aggregate data that has a common key. And you can do it here right within a transform. And again, like any other transformation, this is lazy. It hasn't actually happened yet, right? It'll happen when we shove the data through this thing. And this is what it looks like. It's really easy to use. If you look at the Python version, we're passing a function into the group by command that basically takes an item, in this case a name, and returns the key for that item. This could be anything. In this case, it's W sub 0, the first element. Right? At the bottom, we see a group by, and this is actually not the Scala way to do it. This is the Java way to do it. But it's a similar idea, right? But here, We could transform this some other way. We could create a hash index out of this. We could convert it to a UUID, although that wouldn't be very useful. We could convert it to a number. What it calculates as the key is entirely up to you. So the argument passed to group by is the make this into a key function, basically. Right? And then once you have things in groups where you have keys, there's another thing that you can do. Imagine you have taken, suppose we were to go back to this one, and instead of using a group by on this, there is another way to do this, although it's arguably maybe a little less efficient. I could do a map on this and transform this into what's called a pair RDD. So I could map this into a key and a value. So now the second RDD becomes similar to the first RDD, same number of elements in it, but things in there are associated with keys and values, which looks kind of like this. So here's a case where we've got a bunch of elements in the RDD. They have keys and they have values. 3 items all have the key A. 2 items have the key B. Okay, these could have been names. Right now they're integers. But this is how they appear in the RDD, right? If they're already in the RDD like this, a group by key allows me to do this. So it's essentially the same kind of thing, except the group by key is where you already have a key. Group by is where you want to do the transform this into a key and a value and group in one operation. All right, and here's an example of how to do that. So here we've parallelized a collection of pairs. All right, and then we group by key, and when we print them out, this is what we get, right? We get a collection that isn't so much pairs. Sorry, I lost my cursor. But we get a key and whatever values are associated with it down there at the bottom. You have to speak up. I can't hear you. You want this one?
Yeah, it assumes the first element to be the key by default, right?
Yes. Yeah, although there's a way to tell it, I want to use something else as the key.
Can you repeat that question?
Yes, the question was it assumes the first element is the key, right? And the answer is yes, but you know, as with most things, there's a way to change that. All right, I think for the moment I'm going to skip map partitions. It's a little more than we need to deal with in here, but I encourage you to go look it up when you want to. So here's one where there are a couple of different ways to do reductions by key. All right, so what's a reduce by key? A good example of a reduce by key is I want to count the occurrences of a particular key in the data set, right? So it turns out there are 2 ways to do it, but one of them is more efficient. So if you look at reduce by key, what are we doing? We've got a word pairs RDD. So what we've done is we've started out with an RDD that has some words in it. There's 1 instance of the word 1, 2 instances of the word 2, 3 instances of the word 3, right? And then we parallelize that. And immediately after parallelizing it, we map it into a key and a value. The word is the key, and 1 is the count at that point. Now what we really want to do is find out the total count across the entire data set, which means we have to pull that information. We essentially have to shuffle that information across the network, correlate things by keys, and then do an addition. So when we do a reduce by key, what's going to happen is reduce by key gets called only with paired values from 2 different from the same items that have the same key. So for instance, you call reduce by key, and what it will say is, okay, aggregate all the data by keys, and then sum up all the ones that are associated with a particular key. Well, look, there's only 1 element that has key 1, so I'm never even going to call reduce by key. 1 is the value. There are 2 elements that have key 2, so I'm going to call reduce by key. I'll end up calling it once, and the arguments will be 1 plus 1. Now this underscore business in Scala is just shorthand for argument 1 and argument 2 to the function. Okay, but basically it's going to pass 2 arguments in there in this particular case. The 1's associated with the 2 instances of the 2's. So the result associated with the key 2 will then be the number 2. And then reduce by key in this particular data set will actually end up being called twice for the key 3. The first call to reduce by key will pass a 1 and a 1 in for 2 of the 3 elements and get a 2 out. And then that 2 will become an input to the second call to reduce by key with a 1 from the next one, and that will result in a 3. Now that's the easy way to do it. It turns out that's the more efficient way to do it. You can also just do a group by key. Group all elements by key. We already saw what that did. Put them all together. All elements with the same key end up in the same location, the same item in some RDD, right? Or in the RDD, but in some partition. Then we map those things. This is just weird Scala syntax for extracting elements of a tuple. But what we're going to map it to is the same key, tuple element 1, plus the second element of what comes back from group by key, remember, is a list or an array. All the elements that map to that key. So what will end up going into map will be, for instance, 1 followed by an array containing just one number 1. Then another one will be 2 with 2 element array, 1 and 1. And then a key 3 with a 3 element array, 1, 1, and 1. And this thing sums up those arrays, okay? Now, both of these things produce the exact same value. But the first one, reduced by key, is actually smarter, okay? The group by key is going to shuffle all keys across the network because that's what you asked it to do, okay? So if there are 100,000 elements that have key 3, you're going to move 100,000 elements across the network. And then you're going to do the addition. Okay, but what reduce by key does is it's really smart. It says, okay, I need to move this stuff across the network, but I can do a local partial addition, partial reduction first. So I can do a partial reduction within each partition first, and then what I shuffle across the network is the partial sum, right? And then once I've got that partial sum shuffled across, I can complete the full operation. All right? So while these things produce the same value, the first one is going to waste a lot less network I/O because it's going to be smart enough to optimize and do a local partial sum before shuffling that across the network. So there are things like that you need to be aware of. Initially, when you're playing around in the REPL, you won't see any difference between these two because your data sets aren't going to be very big. But in this particular case, if you're dealing with a huge amount of data, reduce by key is the way to go. All right, and this, I'm not going to spend a whole lot of time on this. This just shows you an example of how this stuff gets moved across the network, right? So you can see that what it's doing is local additions, and then it's actually moving those local additions across the network to correlate by key, and then doing the final addition over there. Okay, so it's a much more efficient way to do it. Versus group by key. This shows you what group by key does, and it's a significantly more network I/O. Lots more data has to go over the network. Okay? All right, what are we looking at time? We're looking at 2:45, so I think now would be a good time to take a quick 10-minute break. All right, and then we'll pick up again. All right, so let's shoot to be back here by 5:03. Slide, you guys all have a copy of this slide deck. I encourage you to go through this, and not only go through this on your own, but this is a fairly decent reference. So keep a copy of this around. It's a good way of visualizing, some of these transformations. So as you're reading about a new transformation that we didn't cover, this can be an aid in understanding it, right? So see if you can keep a copy of this around. But I don't want to spend any more time on this because if I do, we're not going to get to some of the other stuff. We're already a little bit behind. All right, hang on. All right, the next thing we're going to talk about is data frames, and you will get to play with these. Okay, if you can keep the chatter down to a minimum, or if you really need to talk, please step outside. It's hard if I can hear you from up here. I'm sure it's disturbing for the people around you. All right, and it's throwing me off my game. All right, so what we're going to talk about are data frames and Spark SQL at this point. So we're going to walk through them a little bit, and then I'm going to point you at another lab where you can get it, where you can play around with them. Now this lab, for those of you who do not like Python, you'll be happy to know that this upcoming lab is actually in Scala. For those of you who don't like Scala, you won't be happy at all to hear that. So we don't have 2 copies of each lab at the moment. That might be a future enhancement. Mostly you're just going to have to live with the pain, and I apologize for that. Okay, so Spark SQL can read from a number of different sources. These are some of them, right? There are products like Tableau who will use Simba's JDBC, ODBC drivers to talk through Spark SQL. Your application can interact with data using Spark SQL. Now, Spark SQL is a SQL subdialect, right? It's not SQL 92, but it's kind of like, there are a number of examples out there. If you've ever played with App Engine, you know there's a SQL-like dialect that you can use to interact with Bigtable, but it's not really SQL. In fact, it's so much not really SQL, they call it, I think, GQL. So this is, it's very, and Hive is the same thing. HQL is very SQL-like, but it's not really SQL. This is the same sort of idea, right? And then Spark SQL under the covers can talk through Hive. It can talk to JSON. We're going to actually be reading a JSON file. It can use the Apache Parquet columnar storage format. There are a number of different formats it can write out to as well. It's basically providing us another way to interact with our data that might be more convenient for us to work with. There is an entire data frames guide out there. Now this says 1.4 up here. And when I first started looking at this stuff, I was under the mistaken impression that I could only use this in 1.4, but that's not the case. Spark SQL and data frames are in 1.3. There are some differences in the APIs, however. The lab you're going to be doing is using the 1.3 API because that's what these shards are based on. The API changes a little bit in 1.4. Everything will still work, but if you're using, for instance, Scala or Java, you'll get some deprecation warnings. So there are some changes in the API, but nothing dramatic. Just stuff to watch out for. There's a link out here to a blog post. I encourage you all to go read this. This is the blog post from earlier this year that talks about introducing data frames into Spark. Okay, it's worth reading this. It's not very long. Take you maybe 15 minutes to read it. 30 if you let yourself space out and not pay attention. Okay, so these were actually announced earlier this year, and they're inspired by the data frames that are in the R language or by pandas in Python. Okay, data frames are available, however, in all of the supported languages. Right, they're available in Scala, they're available in Python, they're available in Java, and in 1.4 they're available in R. Okay, so what is a data frame? It's a distributed collection of data organized into named columns. All right, so it's like an RDD, except everything has a named column association with it. This is why reading JSON is so gloriously wonderful in data frames, because everything comes in with names attached to it and can be mapped quite easily to named column values. Okay, so a data frame can be, you can think of that about it as roughly like modeling a table in a relational database. Okay, it isn't a table in a relational database, but conceptually we're modeling it like a table in a relational database, right down to the fact that we can use a SQL variant to query it. Right, it's intended to help scale better. It scales from kilobytes up to petabytes. Turns out they're actually faster. If you read that blog article, if you use data frames, the performance of data frames is really surprisingly faster than bare RDDs in a lot of cases. Definitely worth looking at that blog article. A wide variety of data formats and storage systems are supported. It's a state-of-the-art optimization under the covers, state-of-the-art optimization and code generation, okay? And then there are APIs, as mentioned, in all the languages, right? So step one is to construct a data frame. We're actually going to do this in the lab, but this is how you build a data frame. This is one way to build a data frame. Hey, I've got this file full of people data. Presumably this is maybe a JSON array, right? Each array is a JSON object, a JavaScript object, if you want to think of it that way. Each of those JavaScript or JSON objects represents information about a person. Maybe it's their first name, last name, age, you know, and a number of other characteristics. By what we use, we get access to this through the SQL context. So you can see here that given an existing Spark context, SC in this case, we can create a SQL context by just passing the Spark context in there and it essentially wraps the Spark context up in a SQL context. Now, within the REPL and within the notebook that you're using, you automatically will get a variable called SQL context, spelled exactly as the left-hand assignment here, lowercase s, capital C. Okay, so just as the REPL automatically gives you an SC variable, it also gives you a SQL context variable, so you don't have to do this. But you do have to do this, obviously, in a standalone application. From a SQL context, I use, for instance, the JSON file call, which basically says, create me a data frame that will allow me to get access to the data in this people.json file. If you want, you can think about this as saying, look, I'm going to be pulling data from this JSON file. I'd like you to overlay kind of a table template on top of it. So as the data comes in, I want to be able to view it as if it's in a table. It doesn't bring the data in yet, right? It's just like an RDD. And in fact, don't tell anyone, but data frames are really a kind of RDD. Okay, so they behave the same way, right? These are lazy operations. But there are other calls that you can make on these things, as you'll see in the lab. A show, you can display, it says display the content of the data frame, but if the data frame is big, it basically displays a sampling of the data in the data frame. So you can get a sense for what kind of data is in there. And you can see from this that we have an age field, a name field, you know, you get an age that's null, and another age that's 30, another age that's 19. Names are Michael, Andy, and Justin. So this particular JSON file appears to have just 2 columns in it. Okay, once you've got it, you can do other things with it. You can print the schema, right? I just confirmed my inference there that there were 2 columns. But if you know JSON, you know that JSON data can be typed, not typed as strongly as we type it in Java or Scala. But JSON data types include things like Booleans, integers, long integers. Some forms support dates, strings, other nested objects. Okay, so when the data frame is instantiated and the file is read, it determines an appropriate schema for this, right? Okay, the age variable appears to contain a number, so that's going to be a long. The name appears to include a string, so that's going to be a string type. Okay, so now I can see the general shape of this file. You can run a select. This is kind of interesting. It's sort of SQL-like, but it's not using the SQL interface yet. So, hey, data frame, I'd like to select just the name column, please, and show me a sampling of the data from the name column. Okay, so there, just a select call with the column that I want. If you want multiple columns, you pass multiple columns in. Okay, you can also select, this is kind of strange, but it almost looks like a SQL query. I'd like to select the name, but I'd also like to select the age column plus 1. So what it does is it selects all the values of name, and then as it reads in the age column, it transforms it automatically. That's like a map call embedded in there. Transforms each value in the age column by adding 1 to it. So you can see in some ways this is actually a fairly convenient way to query the data. Yes?
The print schema, is it an action that's going to force authoring the data, or is it not going to?
I don't believe so. I believe it's just sampled a little bit of it. Okay? I don't think it reads the whole thing. It doesn't really need to. But I could be wrong. I could check on that. I haven't dug that deeply into it, to be honest. It's certainly not something you would typically do in a program you're actually going to be running, right? There's almost no need to do a print schema on something when you're transforming 500,000, rows of JSON data. Presumably, you've already done that kind of analysis when you were building the program out, and you already know what the schema for the thing is, right? So it's mostly something you're going to use in the REPL, at which point it's a bit less of a concern whether it's going to be reading the data or not. Now here's the SQL integration. This is kind of interesting. So note that I'm doing, I'm getting a data frame by doing a select star from some table. Okay, so it basically allows you to run a SQL query on something that looks like a table, and you get back a data frame to play with it. Right? So there are ways to integrate SQL and thereby data frames with an RDD, but in order to do that, you have to tell the data frame in the SQL API the shape of the data in the RDD. Okay? So there are 2 ways it turns out to do that. I mean, it's not automatic, But you can tell it to infer the schema by using reflection on some of the objects within a particular RDD, right? So pull out some of the data, use reflection on what's in there, and try to figure out what this thing is, and construct a schema appropriately. That's concise and fairly straightforward. And the first argument is always going to be yes, but reflection is slow, and my answer to that will always be slower than reading data from HDFS. Not so sure about that, right? And then the second one is that there is a programmatic interface, if you know what the shape of the data is, where you can say, I've got this RDD, and I've got this API over here that allows me to build out the schema programmatically, and then basically just lay that over top of the RDD and say, look, I need a data frame for this. This is what the data in there looks like. Okay, so now reflection's not used, it's going to use what you gave it and produce a data frame accordingly. Okay, so this is an example of using reflection. Now this is Python, so what does it mean to use reflection from Python in this case? Well, remember, really, this is a Python adapter. The work is still being done in a JVM, right? So what we're doing in here is we're basically pulling in this text file. The text file is being split on commas, so presumably it's a comma-separated value file or something, right? And then we're using this thing called a row, and we're telling, and row is something that you can see comes in from PySpark SQL. So we're basically saying, okay, I've got the parts that I need, all right? And these are RDDs, right? Parts is an RDD, right? So I've done an sc.text file to get back lines. Lines is an RDD. Parts is I'm running a map operation over the lines RDD and getting back parts. That's another RDD. So far we haven't read any data. And now I say, look, people is another RDD. Well, actually, really, it's going to be well, there. So we're going to say parts.map. We're going to pass a lambda in there. We're going to use this thing called row to take apart. And we're going to say the name is P0, the age is P1, and then we're going to use that information to infer the schema. And then once we have that, notice this call to something called register temp table. This, in effect, gives that data a table name, a temporary table name, so that it can now be used in select statements, SQL-style select statements. So now when you do, say, select star from people, what it really means is use the data frame interface to this data coming in, and do the appropriate SQL-ish things as if this were a table, but really it's data coming in from this file. Okay?
But still the underlying RDD is still,
What's that?
the RDD is not replicated this time. Still the people RDD is being kind of used.
In effect, the RDD is still there. It's feeding a data frame, right? And remember, like I said, the data frame is an RDD. Okay? All right, and then here's another example. Now that we have this, we've registered people, we can issue this SQL query, right? Select name from people where age greater than equal 13 and age less than or equal 19. Pull up all the teenagers, right? Presumably because we don't want them driving. So here's a simple select statement. Looks like pretty normal SQL to me, right? And what you're getting back is another data frame, and now you can start doing things like maps over that, just like anything else, and then note that we're calling collect on that, just like we call collect on a data frame, right? So once I've done that SQL query, I can collect that and map on that the same as I do it on RDD. Yes?
Question: if you have a RDD that contains many different columns, let's say, and you want to put it into data frames, can you just select certain ones? Let's say you have something that's like 100 columns deep, and you want to take the first one, the fifth one, and make a data frame out of that. Can you do that?
Sure, you could take that data in and map it down, right? You can map it down to those two columns and then convert that into a data frame.
And if it doesn't have a name, like if the column itself does not have a name, is it possible for you to give it one?
In other words, do
JSON would have
the equivalent of a default if the JSON is missing a name?
Yeah.
I think it comes back null in that case. Okay, I don't think there's any notion in here of being able to say something like you could say in the SQL create table statement where you say, this has a name column, and if it's not there, default to this, right? You'd have to do that with logic, as far as I know. Andy can correct me if I'm wrong, but I'm pretty certain you'd have to do that with logic.
But how would you call it? Would you then just say item 0, like an item 4 to get the first and the fifth?
It's a map operation, isn't it? You're extracting information. You're winnowing down your data set. Okay, so you'd have to extract that through a map first, produce another RDD, and then you could use that to build a data frame, right? You can build a data frame from any RDD if you know the shape of the data. Okay, if you want to, we can dig more into this at 5. Be happy. We'll all be happy to talk to you offline about this. But right now, I want to keep plowing forward, if that's okay. Okay, and then there are examples again of being able to create this via a programmatic schema. Okay, it's usually 3 steps. Create an RDD of tuples or lists from the original RDD. Okay, so take the original RDD and break it down into tuples or lists, some sort of a collection. Right? Create the schema represented by, and this struct type is something that is given to you. There's documentation on this, but basically what you're trying to do is match the structure of the tuples or lists created in step 1, and then you apply the schema via a create data frame method on the SQL context. And here's an example, right? We're going to construct a data frame from a users table in Hive. Right? So we're pulling a table in, pulling in a log file from S3. Okay, these are additional examples of using a data frame, right? So now we've got this users table in Hive, and we've got this log file, right? And now we're creating a new data frame that contains only young users. So you're transforming data frames much the same way you're transforming RDDs, right? Okay, or alternatively, you can use a Panda-style syntax in Python if that's what you prefer, right? And then we're going to increment everybody's age by 1. There's another select statement. So I can select out of this data frame using a syntax like this, but I can increment on the fly. All right, and then I can do a group by. Okay, I want to count the number of young users by gender. Let's do a group by and then do a count on that. Right, I mean, these are all just very common operations that you can do on these data frames. And there's even a join capability. I want to join the logs. So here what we're doing is we're doing the equivalent of a left outer join of the logs against the young users, right? And being a left outer join, of course, if there's no match, we're going to get some empty cells. But we're going to match up log entries where the user ID in a log entry, presumably it's been decoded into something that has a user ID, matched against the user's user ID, but we're joining only against the data in the young data frame. Okay, so at this point, I would like you guys to play a little bit with data frames. So in order to do that, there is a lab out here. Let me pull this up over here so that you guys can actually see it. Now you're going to have to copy this lab. Okay, and I know you can't read this, neither can I. I'm making it bigger. If you look under today's labs, here it is. It's called data frames. You're going to have to clone this into your environment. It's not really big, but it will let you play around with data frames, use the syntax a little bit. There's some SQL in there. There's a way to map the data frames into something you can call with SQL. It's reading a file that's already present out here, but really it's using a capability in the Databricks product that allows me to make what looks like a local file out of something that really resides on S3. So it's essentially going to be pulling the data out of S3 as you go. And there is an assignment in here, so walk your way through this, see if you can understand it. And then at the bottom of the whole thing, there's a refinement. Look, now that we've done all of this in data frames, see if you can do this last thing, which is sort of like a little bit more complicated than the last thing that I gave you in this lab. Really quickly, talk briefly about memory and persistence. This relates primarily to caching. Okay, so a couple of guidelines here. When you're setting this stuff up, it's recommended that you set it up to use at most only about 75% of a machine's memory for Spark. Okay, these are guidelines. What I'm not telling you is exactly how to implement this stuff. We can point you to some documentation on how to do that. Your minimum executor heap should be about 8 gig. Now, just a brief terminology here: driver, worker, executor, etc. What do these things mean? All right, so in a standalone cluster, the driver is your program, right? A worker is basically, you can think of that as owning the resources, owning the executors on a particular node. Okay, you could, in theory, you can have multiple workers on a given node, but a worker is responsible for allocating executors based on what you ask for. So a driver wants certain resources, it contacts the workers and says, hey, I need a certain number of executors with a certain number of, a certain memory size, a certain number of cores, meaning slots, certain amount of work threshold, and the executors are spawned by the worker. The executors then contact the driver, and then they work paired up with that driver for the duration of a series of jobs. Okay, so your minimum executor heap you should keep at a minimum of 8 gig. All right, the maximum depends. You know, 40 gig is generally good, but watch out for garbage collection. Right? Yes.
If I have a machine with, say, 128 gigs of memory, can I set that higher, or is it going to be an issue?
In general, you want to be careful how much memory you give a particular Java VM, right? If I recall correctly, once you get up about 40 gig of memory on a Java VM, it doesn't matter how much RAM you have on the system, things get kind of weird. You know, garbage collection gets strange. So in that case, you would probably actually want to maybe split it up into multiple workers with their own executors, right? Or set an individual worker up so that it spawns multiple executors of smaller sizes. Okay.
Does Spark support that as some command line switch to tell?
Yeah. Again, it's kind of beyond the scope of. That's what we're getting into, like operations. It's kind of beyond the scope here. Mostly these are guidelines for when you start deploying this stuff. We're not going to talk really deeply about them here, but remember that these are guidelines, and that as you start getting into, like as I said to somebody offline, kind of the purpose of this class is to get you used to using the Spark API, right? So at which point it's a little premature while you're trying to get used to using the API and using the code base to worry too much about how you're going to deploy it. Once you get into that, now it's time to do some DevOps research, so this stuff becomes a little bit more, you know, something you have to worry about more, and then how do I do this? And there are courses that are offered that can help with that, and there are tutorials out there that can help with that. Okay, so there are a number of different ways that you can serialize data, that you can cache your data, right? There's in-memory only, and then there's memory spilling out to disk, and you can control that with some switches on when you choose, for instance, to cache an RDD. Where does it get stored? Okay, so you can force memory only if you know this is small enough to fit in all of memory. So at which point the contents of the RDD will be stored as deserialized Java objects in the JVM, native Java objects. They're stored purely in memory. Okay, you can do memory and disk. So what will happen is that they will be stored as deserialized objects in memory, but if the amount of memory allocated to the cache fills up, then it will serialize them and spill them out to disk, which still might be faster than rereading them from the data source, right? You can use memory-only serialization, so keep it in memory, but serialize them. You can use memory and disk serialization, so if it doesn't fit into memory, spill them out to disk instead of recomputing them on the fly whenever they're needed. You can actually have RDD partitions stored only on disk. Right, and then there are replication options here. Memory only 2, memory and disk 2. Basically, I want to store this stuff in memory only or memory and disk, but I also want I want it to be replicated on some other partition in another cluster. Right, so you've got some level of replication, so that in case one crashes, you've got a copy of it serialized somewhere else. And then there's an off-heap storage. All right, so that it's stored outside of garbage collection in Java. So it's actually stored elsewhere, serialized and stored in memory, but outside the Java heap, and therefore not subject to garbage collection. Okay, which can be faster, right? Because you're completely outside the whole GC, scan, mark, and sweep. All right, so here's one way to set up a cache. Right, RDD cache is just shorthand for RDD persist memory only. Okay, but there are other ways to do this, and when you do a persistence like this, right? Now, the way this works, this says memory only, but what this really means is store the RDD as deserialized Java objects in the JVM on heap, but if the RDD does not fit in memory, the extra partitions that could not be cached will be recomputed on the fly as needed. Okay, which is kind of interesting. Some of the data will be recomputed by reading from the parent RDD, which may in turn read from another one. Some of it's cached. Okay, that's as distinct from spill the extra ones that don't fit out to disk. Okay, when you put this stuff in place, for instance, in the Databricks product, you can actually go into the storage tab in the UI and take a look and see where this stuff has been serialized and how it's been serialized and how much room it takes up. Okay, so here's another one. I want to persist this in memory-only serialization. So store the RDD as serialized Java objects, 1 byte array of them per partition. This is more space efficient than deserialized objects, but if you're using this, you're paying the serialization penalty, right? And by default, we're going to use, Spark is going to use native Java serialization, which isn't all that fast. But you can substitute something like cryo, right, which will speed up your serialization significantly and may make this a perfectly reasonable option for you. Right, and here's a case where the stuff is stored, again, in memory, deserialized, but if it's not able to fit in memory, then those that don't fit are serialized and written to disk. Okay, but it's on a partition basis. Right? So if it doesn't fit in memory, the whole partition will spill out to disk. It's not portions of the partition. Fit it in memory. If it won't fit in memory, put the whole partition on disk. Okay, so you can see a graphical example of that there, right? This is similar to memory-only serialization, but the spill partitions that don't fit in memory the partitions that don't fit in memory are spilled to disk instead of recomputing them, okay? And they're serialized. I believe this one is not serialized, right? But there's a note in here that says we need to figure that out. Okay, and then this is pure disk. Okay, this is similar to storing it in memory serialized, but go to disk, store it on disk, instead of recomputing them. Either way, you're not recomputing it. Okay, so you've got, the point of this is not that you should memorize all these options, but that you should realize there are loads of options out here for how you want the cache to behave. And you'll need to do some performance analysis if you're trying to speed things up. But oftentimes, even if you're storing it in the slowest possible manner, it's going to be faster than recomputing it from the original data source. Okay, so that's a brief overview of this. I'm going to skip through this. I want to make sure we get to some of the other stuff. This is the persist off heap, by the way, where it's actually being persisted as serialized data in Tachyon, which reduces your garbage collection. And somebody asked earlier, you know, if I've got cached data, can I tell it to go away after a while? Like, is there a way to set a cache expiration? The answer is, as far as I know, not directly in the API, but there is an unpersist call. You can uncache an RDD. So you could certainly set your own timeout to do that, I suppose, right? Wait a certain amount of time and then decide, okay, unpersist, right? So if you want to do that, you can manage that yourself. It's not that difficult. But you can uncache an RDD, which is useful to know. Okay, and it uses an LRU type of queue to figure this out. So it monitors cache usage on each node, and old data gets dropped out in at least recently used fashion. Right? So if you want to manually remove an RDD instead of waiting for it, you can unpersist it. But RDDs can be tossed out as another one gets cached based on an LRU algorithm. You know, you're caching more RDDs than you can possibly cache on that node. It'll throw the old ones away. Right? So that's just a brief overview of some of the memory management stuff for caching. I want to spin down here really quickly before we run out of time and take a brief look at Spark streaming. Okay, and again, we're going to kind of just skim through this, but it'll give you an idea of what can be done with it. All right, so the general idea behind Spark streaming is that you've got streaming data coming in from a variety of different places. It could be HDFS, but oftentimes it might be a TCP socket, right? You can imagine live stock data, for instance, or something that's coming in as a stream of data, right? So you need to somehow manage this through Spark. And maybe you want to dump it into HDFS, maybe you just want to process it, maybe you're doing video analysis, maybe you're doing some other kind of analysis of information that's coming in as a stream. So the point behind Spark streaming is that it enables you, I'm going to skip ahead here, it enables you to, these are some use cases for it. Let's back up. Okay, so live statistics, pulling page views off and buffering them through Kafka and then using Spark streaming to process the information. Maybe reading live smart meter readings, right? Buffer those through Kafka, pulling in live weather data through Flume, and then using Spark streaming to join those two pieces of data together so that you get some way of plotting the meter readings against the weather data. Right, and so essentially what's going on here is think how Spark Core works. Spark Core works in terms of RDDs, which you can almost think of as buffers of data, right? But streams aren't buffers. Streams are bytes coming in at some pseudo-regular interval, but the rate, it can be bursty, it can come in fast, it can come in slow, there can be lags. So the idea is that what Spark Streaming's job is to do is to take this incoming stream of data, this fire hose of data, and break it up into batches of RDDs, which it then feeds into Spark Core for processing. So how it does this basically is entirely time-based. Okay, so as the data comes in, there's this receiver thread, and the receiver thread basically buffers up data until a certain amount of time has elapsed. And when that time has elapsed, whatever data is there, it gets turned into an RDD and shoved into Spark Core for processing. All right, so your RDD might have a large amount of information in it during one cycle, and the next cycle it might have less information in it, because whoever is on the other end of the VoIP line stopped talking, for instance, or the streaming data stopped coming in because of TCP congestion or something. So essentially this is a blocking approach. I've got data coming in, I need to block it up, process it using RDDs. All right, so it's building a batch every so many seconds. And then those batches just goes through Spark Core as RDD, same as anything else. All right, and the basic way to manage this stuff is what's called a discretized stream or a D stream. So you have an input D stream like this, which represents the incoming data, right? And it's blocked like this, based on timestamps. Okay, so we've assembled 3 blocks together in 5 seconds because that's our time slice. So that block then gets built up into an RDD. All 3 blocks are in an RDD. So we have 3 blocks of data, we have 1 RDD, that RDD can now be processed, and then 5 seconds later we might get another RDD. It might have 3 blocks in it, it might have 5, right? But this is how it's getting broken up. And then those RDDs, basically with Spark Streaming, you're actually putting your filters and your transforms, you're actually going to put those on the D stream, not the RDD, because these RDDs are coming and going. So it's not like creating an RDD programmatically. I have the RDD now, I'm going to attach a transform to this RDD, right? These RDDs are coming and going as data comes in, being created dynamically depending on the amount of data streaming into you. So you actually attach your transforms to the D stream, and essentially what happens is that as the RDD gets created, then those transforms get applied to the RDD as if they had been created on that RDD, right? And they feed more, you have multiple, you're essentially creating these D streams as your chain of things. But under the covers, those things are dynamically creating a chain of RDDs. So you can see what's going on here. We have a base RDD, a base D stream, this lines D stream, and we've created a flat map over that to create a words D stream. Well, as a new RDD comes in, we essentially, under the covers, get an on-the-fly created lines RDD. The flat map gets applied to that, and under the covers of the words D stream, then you have an on-the-fly created words RDD. So you can see how it's sitting on top of Spark Core. So it's allowing you to use the standard transformations, and actions on an RDD, but within data that's coming in continuously. Okay, so here's an example that I find very hard to read. Okay, but, and this is a Python example. I think it's hard to read because it's my screen. So here we have a local streaming context. built out of a Spark context. Okay, 2 working threads and a batch interval of 1 second. What's the batch interval mean? Means that as the data comes in, every second we're going to stop and create an RDD out of the incoming data. Right, and then we're going to create a D stream to connect to this port where we're going to be reading the data. All right, so presumably the data is coming in on localhost 9999. I'm not sure what's running in there to generate this data. But then we're going to split each line into words. So there's our words D stream. So you can see we're doing the maps on the D stream. Right? And then we can count each word. We're going to create a pairs D stream out of the words D stream by mapping each incoming word to its to a tuple containing the word and a number 1. This is a standard word count, but we're streaming. It's a streaming word count. Right? And then at the bottom, then we can do a reduce by key. And here we're, this words count dstream pprint is going to print, in this particular instance, 10 elements of the RDD to the console, right? But presumably what we might really be doing is streaming this data someplace else. But this is a case where you're just watching 10 of these elements come up on the screen to see what's going on. Now at this point, nothing's happened yet, right? It starts happening when we do an SSC start. So that starts the computation, all right? Now this computation is going to be occurring under the covers using future-driven future-driven thread pool. So you don't want this thread to go away, or that's just going to kill everything. Hence the await termination at the bottom. Okay, so we're going to do an await termination, and then this all becomes event-driven. This stuff starts to happen, right? pprint is, in effect, an action that's happening, but it's happening every time we process a new RDD. So every RDD that comes in is going to go through this series of things and then have the first 10 elements printed. And we're just going to sit there and keep going until one of several things happens. Somebody hits Control-C, kills the thing maybe. The other end of the socket connection shuts the socket connection down, right? Eventually, or somebody kills the all the threads that are running underneath. But eventually, if all those threads were to finish because the socket shut down, then the await termination would return and your program would end. Okay, so it works a lot like RDDs, except that the way you have to think about it is that you're not actually putting these things on RDDs. You're creating almost a template for how these RDDs will get created, right? You're building up this stream. It has its own DAG, right? But that gets applied to each RDD as it gets created from the incoming data coming in. So you're taking a stream of data, creating blocks. The blocks then are having these transformations put on them as defined by the D streams that they're being fed through. Okay, so it's pretty easy to use.
Quick question, can you apply all the transformation on dstream as you can on the RDD?
The answer to that is, off the top of my head, I don't know. I believe so, but go look at the API docs, okay? I'm pretty sure that they're there, but the API docs will show you for sure. Right, so here's an example of somebody actually doing this sort of thing, right? Using netcat and telling it, listen on port 9999, and then when somebody connects, send hello, hello world, right? And then the previous program is put inside something called network word count, and it's run like this, right? Or something similar to the previous program. Actually, these arguments don't need to be passed in here. So this is the previous program. Arguments are ignored. This thing comes up, connects to localhost 999, and you can see what it retrieved here. It printed hello to world 1. But if this were a real example, you might have this netcat thing dump a whole bunch of data upline. I could imagine taking this same word count thing and connecting it to something that just sits there and generates words and spews them upline, and let's see what happens. It would be relatively easy to do that. It's not that difficult to write something like that. Or just cat some very large file, or dev urandom, into netcat, and dump that upline and see what happens. Yes, in the back, please.
When it goes to each period, would it put a new timestamp and then show the words if you kept throwing stuff into netcat?
Okay.
Over time, would it just put a new timestamp there?
I think that timestamp is actually being printed out by pprint, I believe, but I'm not positive. But I mean, if you think about what would happen is, each time this RDD gets created, then and we're summing things up, right? but that's really a partial sum because there's still more data coming in over the stream, right?
Or I think it's as more data comes in, but it's been blocked out, blocked different, time chunks. Is it just going to keep printing ongoing?
Will this count increase? Is that what you're asking?
No, I know it will increase because it's already printed the screen and it's a different RDD, but every time it blocks it out, it's creating a new section of keyprint.
So I guess the question is, what would the printout on the screen look like if you have a Latino screen words coming?
In this particular case, I think you're going to see a timestamp with up to 10 of those elements every time, right? A new timestamp and then 10 elements out of that RDD. Again, play with it. I haven't played with pprint. I don't know that that's what's happening here, but it seems to me that might be what's happening. You could also do a collect or some sort of a sample of the thing and print those to the screen as well. I think that's all pprint's doing. First 10 items, dump them to the screen.
The most recently updated items, right? The most recently updated items, you're going to get the top 10 of those, right?
What you're getting are the top 10 items out of the RDD that was just created, okay? So you're asking me if it's the most recently created ones? Again, you have to think about this stuff as what's happening is blocking, okay? So you've got a fire hose of data coming in that's broken up into chunks, okay, by the receiver thread of the D stream. So this huge amount of data coming in. Every so many seconds, that's getting broken up into an RDD. That RDD gets processed just like any RDD that you played with earlier, okay, top to bottom. The things that its DAG, its list of instructions, come from the D stream, right? So whatever you attach to the D stream gets applied to that RDD, and under the covers is producing other RDDs, right? Now at the end of this, any action that you take on that, including a pprint, gets executed, and then we're done with that RDD, right? So if you didn't save the data, of course, now the RDD is gone, right? Maybe you dump that data into Cassandra. Maybe all you're doing is dumping a sampling of it, right? But at that point, it's gone. The RDD is gone, the data is gone unless you saved it. But presumably there's another RDD with the next hunk of data that got pulled off the wire, and then it's going to go through the exact same process. So it's almost like you have a big loop around code that's constantly creating an RDD and doing something with it, and then throwing it away, going to the top of the loop, and then doing another pass on it, right? So that's kind of how you have to think of this. It's one big continuous loop, and what's being fed into it is RDD after RDD after RDD, which is coming out of the stream data. Take a chunk, wait up to however many seconds we have the size set to, the batch size. Okay, pull out an RDD, throw that into the loop, let it run through that RDD, and then, presumably there'll be another one ready by that time.
And while it's stopped, it didn't stop, but while it's processing the first, there's another RDD that's getting, basically created and queue right behind it, right?
A little louder, please.
Well, so your time limit expires if you've got an RDD that's matured or populated and ready for processing.
Right.
And while you're processing that, you've created another RDD and captured those additional events that'll be processed in that loop next, right?
Yes, and in fact, that's actually an issue that you have to worry about, as one of these slides down here shows, which is here. This series of slides here is intended to give you a sort of a pictorial representation of what's going on, right? So we got a batch interval, 600 milliseconds. Data comes into the receiver thread and is chunked out to individual executors, right? And then we have another one coming in, that gets processed. Then a third one coming in, that gets processed, might go to different executors. And then now we have a situation here. This guy is being processed. A whole bunch of stuff has been put in here. Okay, so there are, we have actually batch intervals. We've collected a bunch of them up. We're now processing them, okay? As you're processing them, another one is coming in. If the time it takes for you to process the things that have already been distributed out to the cluster is longer than it takes for the next set of things to come in, you're going to start falling behind, right? So it's exactly that. It's queued up, right? You have a certain amount of them you're going to process within a batch window, and then you're processing them. And meanwhile, the receiver is buffering more of them up, but it can't give them to you yet because you're busy. So you've got to be careful how you set this stuff up so that you don't have data coming in so fast that you're getting behind, right? So that's essentially, it sounded to me like what you were asking. Yeah.
I have a question. So if we need to drop something like something, so like
I'm not sure what you mean. You want to drop stuff out as it's being received?
There are some words more frequently. So I only want to keep those words. So you do a filter somewhere here. I want to keep words happen frequently. Like 5 times a second. And drop everything else. How are we going to do it here?
Well, I mean, you could do that with a filter, but right.
But where?
It would be on the D stream, right?
D stream, how do we do D stream? They're not even counting.
I think maybe this is a question we should take offline.
Okay.
Okay? Hit us up at 5 o'clock and we can point you in the right direction for that one.
Is it a simple answer where you filter it and keep a count and count to 5?
Well, I think the problem is, of course, he's talking about things like, per second, right? I only want to keep ones that are occurring so many times per interval, right?
So you have a window of 5 seconds to filter.
Right, but the problem is that the code processing the RDD doesn't necessarily have that window. It's giving an RDD and it's running it, right? Right, there's no, right, it doesn't. It has no concept of history. So you essentially you would have to store that someplace and then check on it somehow.
Drop within that window. Within that window, this is less than five counts. You drop.
You could do that. That's just a pure filter. Within that window means within a particular RDD. So what you would do is, if that's what you're interested in, is I don't want to keep any data within a particular processing window that is less than 5 numbers of them. That's just a simple filter on that RDD, right?
But where? Which line?
Well, so the problem is that, again, if you go back to this code here,
Yeah.
which I've got to get back here, got to get through the animations. Okay, look where the filters are being placed in this code. They're not being placed on an RDD because you're not operating on an RDD here. You're operating on what's known as a D stream. Okay, what is a D stream? That's an abstract representation of the stream of data coming in. It isn't the data, though. What it is, you can almost think of it as assembly instructions for the RDDs that are coming in. Okay? So you can basically say a particular D stream will have certain transformations on it. Conceptually, what you want is to apply these transformations to the streamed data coming in. You with me so far? So as data comes in, I want to filter some of it out, right? You get, all right. But the problem is, of course, the data isn't really streaming into anything other than the receiver thread. What's happening is the data is coming in and being buffered into an RDD. You with me so far? So that RDD then is your buffer full of data. So what you're saying is, I want to be able to say for a given buffer full of data, I want to throw out anything that has fewer than 5 instances of a particular key, let's say, right? So what happens here is that you would add a filter to the D stream, okay? That basically, after you've summed the count, at the bottom here, you would add right after the reduce by key, you would add a filter to the word count D stream that would drop anything that has a count of less than 5, right?
Because underneath is RDD going.
Yes, but remember, that's only going to drop those that are fewer than 5 within that RDD, right? So maybe you'll drop stuff that would have had more than 5 if you just waited for the next RDD, right? It's a risky maneuver, right? Because it depends on how your data is clustered coming in, right? You may say, oh, look, I've only seen this key once in this RDD, let's drop it. Next RDD comes in, it appears 4 times. Well, you're going to drop that too. But really, you just saw that one 5 times, right? But you saw it 5 times across 2 different RDDs, and you dropped it both times because any individual RDD is applying a threshold of 5, right? So and that might be fine for what you're trying to do. But if what you're trying to do is to aggregate this stuff across RDDs, you're going to have to persist that information somewhere and consult that, during the processing phase. But again, it depends on what you want to do. The key is to realize that even though this looks like you're processing data in a stream bit by bit as it comes in, you're not. You're processing a buffer at a time, right? And you have to be aware, unlike reading a file, where, you know, the buffering is done for efficiency. Here, you have to be aware of the buffer boundaries if in cases like that, because they can change the way you process the data, right? Okay. That's, we don't have a lab for D-streams really here. But there are some guides out here. If you decide you want to set this up, right? So there's some basic streaming where you're just reading from a file system or a socket connection. Okay, so essentially in this case, it's like attaching the socket directly to your program, and the data flows in at whatever rate it flows in. But you may want to buffer the data coming in using something like Kafka, right? And so there are guides for how to do that, right? You can also build your own receivers. That's pretty advanced. You can do it, and we're not going to talk at all about that. But if you need to integrate with Flume, or you want to integrate with Kafka, there are guides out here on spark.apache.org to tell you how to do that if you need to use buffering because the data is coming in too quickly for you. Okay, and here are some of the transformations available on D-streams. So they look a lot like the transformations available on an RDD, not surprisingly. And here's some of the output operations available on them. There's the print. I think that was really just print. I think it was a typo. You can save as text file, right? This is basically going to save the information of one of the RDDs in a text file for you, although really it could be multiple text files. Save as an object file. Okay, so here we're serializing object data to disk. Save as Hadoop files. You can loop over things. Okay, so again, take a look at the documentation for output D streams and see what you can do on those. Okay, and then finally, I think we've got about 20 minutes left. So I think I'd like to actually have you guys play a little bit more in the labs, unless there's a hue and cry against that, because we do have a couple more out here. If you'd prefer not to do that, everybody scream, but there is underneath. The reason I want to do this is I'm kind of a firm believer in that you don't really understand something you don't code. So what I was going to suggest, I think this is the wrong shard. Hang on just a sec. There should be a lab out here for, yeah.
We are here not to learn syntaxes. We are here to learn those architectural, conceptual level. If you can present, more at conceptual, architectural level on the next concept, that will help. We are not here to learn syntax.
Okay, so is that the general view then? Nobody wants to do any labs? So you guys would rather do some labs? Okay, we'll do a poll here. Hands up for labs. I think that wins. Okay, I think that wins. All right, so there is a DevOps 2 in here, and that's the one I would recommend that you take a look at. All right, we have about 20 minutes to go through this, and I just dragged the wrong thing over here. I'm sorry. So again, this is something you're going to have to clone. We've got too many windows here. But it's under the Today's Labs area. This says time to complete 30 minutes, but I don't think obviously we don't have 30 minutes. But it's just some more things to look through in here. Importing a text file, for instance. Running transformations on the thing. All right, looking at some other operations like take. Checking the number of partitions. I would also recommend that as you do this, take the opportunity to pull up the UI and see what you can see in there as you're running this on your cluster. So if I were to move this over into my area, see if I can find Class East 1. I think I have an instructor folder here. Okay, so I'm still waiting for this to come up. This is Class East 1, but underneath here, when you attach this to whatever cluster you're going to use and you run it, then you'll be able to pull up the UI. Take a look at some of the things that you can do. Wow, what's with this scrolling here? Let's do this. As you start running these things, you can pull up the Spark UI here and see what jobs are running. Maybe try caching a couple of RDDs and see what show up in the storage tab. Right, and I'll walk around, and if you have problems, just let me know. Yeah, that's sort of beyond the scope here. There is the answer. The answer really is within here. It's possible, but by the time I describe it to you, we're going to be out of time. But basically, I had to do this last night, and there's a description on how to do it. You can basically put a file out on S3, for instance. The easiest way to do it: put a file out on S3. There are ways to set up your credentials in here so that you can then say, look, I want you to mount this S3 file under one of these DBFS locations. And then once you've done that, you can open that as if it's a file, which is what we've done with these things. And I can show you offline how to do that, but obviously you're not going to be able to do it in here unless you already have the file out in an S3 bucket somewhere and you've applied all your credentials to this environment and that sort of thing. If you want, remind me when we get to 5 o'clock and I'll show you the code that I have that does that. It's not hard, right? And then you just shove whatever you want up in S3. That's really the easiest way to do it.